In this video, we're going to talk about mass, length, and time. Here are the objectives for this unit. Record data using scientific notation. Record data using International System of Units, or SI units. Let's check to see what you already know. Express the following numbers in scientific notation. Go ahead and record these 4 numbers in your notebook and write them in scientific notation. If you're unsure what to do, that's okay. Just do your best. Pause the video now. Number 2. Which of the following data are recorded using International System of Units, or SI units? Select all that apply and write them in your notebook. Pause the video if you need to. Here are some physics terms you will need to know for this lecture. Measurement, matter, mass, length, surface area, volume, density. On the next slide, we have scale, macroscopic, microscopic, temperature, scientific notation, and exponent. If you do not know what these words mean, please make sure you get the definitions into your notebook so that you can review daily. We will mention the equation for density. Notice this equation is rho equals mass per unit volume. That P is not actually a P, it's the Greek letter rho. Physicists commonly use the International System, or SI, units to measure and describe the world. This system consists of 7 fundamental quantities and their metric units. The 3 fundamental quantities needed for the study of mechanics are mass, length, and time. Mass describes the quantity of matter. So for instance, if we heard, the store had a massive blowout sale this weekend, how is the term massive incorrectly used in the physics sense? Why is it incorrect? Can you suggest more correct words to use? Go ahead and write those in your notebook now. If you need more time, pause the video. Length describes the quantity of space, such as width, height, or distance. So if we heard the following sentence, how long are you going to be in the bathroom? How might the word long be misinterpreted in the physics sense? Is the speaker talking about length? Can you suggest more correct words? Go ahead and write those in your notebook now. Pause the video if you need to. Time describes the flow of the universe from the past through the present into the future. In physics, this will usually mean a quantity of time in seconds, such as 35 seconds. In everyday language, you may hear, "What time is it?" How is the meaning of time in "What time is it?" different from the meaning of time in "How many seconds does it take to get across the room?" To the questions in your notebook. Pause the video if you need more time. Each of these 3 fundamental quantities has its own SI unit. What are the SI units for these 3 quantities? Think about it. Can you guess what any of the other 4 fundamental quantities are? Here we can see Table 1 from the textbook. It lists the physical quantity, quantity symbol, the fundamental unit, and the unit symbol for your International System of Units. Mass has the quantity symbol of M, the fundamental unit of kilogram, and a unit symbol of kg. Length can be written as X, D, L. I've also seen it written as Y and Z, and also S in calculus-based textbooks. The fundamental unit for length is meter. The unit symbol for meter is M. Time has a quantity symbol of lowercase t. It has a fundamental unit of second, and the unit symbol is lowercase s. Electric current has a quantity symbol of capital I, its fundamental unit is an ampere, and the unit symbol is a capital A. Temperature has a quantity symbol of capital T, a fundamental unit of Kelvin, and the unit symbol for Kelvin is capital K. Luminous intensity is a quantity symbol, has a quantity symbol of capital I sub V. The fundamental unit is candela, and the unit symbol is CD. The amount of a substance has a quantity symbol of N. The fundamental unit is a mole, and the unit symbol is MO. All matter has mass and takes up space. A solid rock is matter, but so is gas and liquid. Both have mass. With your hand out the window of a moving car, you feel matter in the air pushing against you. Mass is an intrinsic property that measures the quantity of matter in an object. Your mass does not change if you go into space. Weight is an extrinsic property that depends on the gravity force acting on you. Your weight does change if you go into space. Objects with more mass are more difficult to speed up or slow down. This property of mass is called inertia. These are two balls and they have the same size. Which would be easier to throw? That's right, the beach ball would be easier to throw. Can you describe the concept of inertia without using the word itself? Think about making things move. Think about making things stop. Think about making things change direction. At this time, pause the video and answer the question. Describe the concept of inertia without using the word itself. To fully describe a quantity like mass, you must provide a value and a unit. This object has a mass of 2 kilograms. The value is 2. The unit is kilograms. In the SI system, mass has units of grams and kilograms. 1 kilogram is equal to 1,000 grams. For size comparison, 1 dime is about 1 gram. 2 nickels, about 10 grams. Those steel nuts are about 1 kilogram, the rock, 1 kilogram. You can also measure 1 kilogram of water. Notice though, you can't measure it that way. You'd actually have to have it in a beaker. And then notice that 1 kilogram of air is much, much, much larger than the scale itself. A triple beam balance is an instrument for measuring mass. The scale in a doctor's office is similar in function, but typically only has 2 beams. Each beam has a sliding mass used to balance the load. Length is a fundamental quantity. There are 2 common systems of length units you should know. The English system uses inches, feet, and yards. The metric system uses millimeters, centimeters, meters, and kilometers. The meter is the SI base unit for length. Time is a fundamental quantity. The SI unit of time is the second. Here are some time equivalents. 1 millisecond is equal to 0.001 seconds, or 10 to the minus 3 seconds. 1 minute is equal to 60 seconds. 1 hour is equal to 60 minutes, which is 3,600 seconds. 1 day is 24 hours, which is 86,400 seconds. 1 year, which is 365.24 days, is equal to 31,579,200 seconds. When working with mixed units, you need to convert all to the base unit. So before calculating, you should always convert values into a single unit. Notice here we have 2 hours, 20 minutes, and 9.2 seconds. We convert the 2 hours to 7,200 seconds, the 20 minutes to 1,200 seconds, and then we add those two to the 9.2 seconds. That gives us 8,409.2 seconds. Notice how all the units are the same and they are all the base unit of time, which is a second. If you access your online textbook, you can go to page 46 and you'll see an icon in the bottom there that will allow you to convert mixed units. This makes it pretty easy when solving problems for homework, but don't get too used to it. When you take your AP exam or my exams, you will not be allowed to use this function. When you click the icon, you'll see this screen here that'll pop up. It'll actually be a pop-up window. And what you do is you just type in the number that you want to convert. So for instance, how many seconds are there in 365 days? Go ahead and enter 365 for the days. Here you can see the online calculator gives you an answer of 31,536,000 seconds. So the online calculator is really neat to use. However, you have to be careful in getting too used to using it, because when it comes to my test and the AP exam, you won't have this available to you. So let's try another one. How many minutes and seconds are there in 0.685 hours? So go ahead and type in 0.685 hours in the box. The pop-up window will actually give you the answer, which is 41 minutes and 6 seconds. In order to keep practicing these conversions, if you click on C, D, and E on the letters below, you can go ahead and practice some more. In physics, we always have the problem of scale. Physical objects and measured quantities have vast variations in size. We measure all the way down to actually the smallest in the nucleus. We actually measure to the size of protons, neutrons, and quarks. And then we go all the way up, even further than the distance between the Earth and the Sun, all the way to size of our galaxy and the universe itself. So when we're looking at measurements that are really, really small or really, really large, and they're not just the measurements that we would take in everyday life, we have to express those very large numbers and very small numbers in a different way. When we talk about macroscopic scale, we're going to be talking about our everyday, ordinary life scale. When we talk about atoms and molecules that make up matter, or even going smaller than that, we start talking about the nucleus and the electrons, or even the quarks that make up the protons and neutrons, then we're talking about the microscopic scale or the quantum scale. Scientific notation allows us to talk about the sizes of things that are very large or very small. Scientific notation is a system that makes it easy to work with those huge numbers that are needed to describe the physical world. It also helps us to describe very small numbers as well. So for instance, if we have 4.3 times 10 to the 3, this is a very large number that's been expressed in scientific notation. This number is simply expressed with a coefficient multiplied by a power of 10. For this example, the coefficient would be a decimal number between 1 and 10. Notice here it is the 4.3. The powers of 10 could be 10, 10 squared, 10 cubed, 10 to the 4th power, and so on. In this example, it is 10 to the 3, or 10 to the 3rd power, which is 1,000. For numbers less than 1, scientific notation uses negative exponents. So for instance, if we have the number 0.0015, it's really 1.5 divided by 1,000. Well, 1,000 is represented as 10 to the 3. So it's really 1.5 divided by 10 to the 3rd power. When you divide by an exponent, you can actually multiply by subtracting it. So we end up with 1.5 times 10 to the minus 3 instead of 10 to the 3 in the denominator. So negative exponent means number smaller than 1. Positive exponent means greater than 1. Here are your powers of 10 that you need to know for this course. We start with the smallest, which is femto, and move all the way to the largest, which is tera. Notice that all of them are going by powers of 3 except for centi, which is 10 to the minus 2. So I've just memorized that centi is 10 to the minus 2 and kilo is 10 to the 3. From that, I just count by threes. So mega has to be 10 to the 6, giga 10 to the 9, tera 10 to the 12. I just add 3 as I go. Starting below centi, since centi is 10 to the minus 2, that means milli must be 10 to the minus 3, then 10 to the minus 6, negative 9, negative 12, negative 15. You always go by threes except for centi. Now there's a mnemonic which will help us to learn how to remember the order of these powers of 10. So here's the mnemonic. Tom got mad, killed cheating married man near pretty females. I didn't come up with this. My students from long ago invented this. If you want to come up with something different, by all means do so. So Tom is for tera, got giga, mad is mega, and so on all the way down to femto. So all you need to remember is Tom got mad, killed cheating married men near pretty females, and remember that everything goes by threes, and you'll have it down pat. A lot of mistakes that I see that are being made on tests, especially when it comes to calculating very large or very small numbers, is how to put those powers of 10 into the calculator. A lot of students will actually put in the times, the 10, the caret for the power, and so on. The problem with that is that if you don't have your parentheses in the right place, you end up having the wrong answer. So here's a quick way in order for you to determine or to enter your scientific notation into your calculator. What you're going to use is the EE button. On your TI-83 or TI-84, you're going to hit second comma, and that is your EE. Then all you do is type in the power. You either put a positive number or you put the negative and then the number that you're going to use for the exponent. Okay, so it's very easy. So you would type in 6.5 second comma, which is EE, and then you would type in 9, and that would give you 6.5 times 10 to the 9. If you wanted to enter a negative exponent, you would type in 2.6, hit that second comma, which is your EE button, and then you would type in the negative 5. It's much, much easier. The calculator already knows that this is a times 10 to the, and it makes it much easier for you to get your calculations done. This also saves you on keystrokes, which you may not think that that's a lot, but when you're typing in 50 to 100 of these numbers, it can actually save you quite a bit of time using the EE button. Now let's talk about derived quantities. We've already spoken about the fundamental quantities. All quantities in physics are either going to be fundamental quantities or they're going to be derived quantities. Mass, length, and time are, remember, our fundamental quantities. Speed is a derived quantity that is calculated from other fundamental quantities. Speed is derived from what two fundamental quantities? Can you think of any other derived quantities? As you may have already guessed, speed is a length divided by a time. Therefore, the units are going to be meters per second, which are the base units for length and time. Density has the dimensions of a mass divided by a length cubed. This would give us the units of mass, which are kilograms, divided by the length cubed. The base unit for length is meters, so it would be kilograms divided by meters cubed. Now we're ready to take that assessment again. Express the following numbers in scientific notation. Write them in your notebook. Pause the video if you need more time. For A, the answer is 2.75 times 10 to the 2. For B, it is 1.73 times 10 to the minus 3. Notice we've moved the decimal place 3 places to the right. That means we've taken a number less than 1 and made it equal to a number between 1 and 10. That gives us a negative exponent. 93,422 can be rewritten as 9.3422 times 10 to the 4. Notice we've moved the decimal place 4 places to the left, taking a number greater than 1 and making it between 1 and 10. For D, it's 1.8 times 10 to the minus 5. Now for question 2. Which of the following data are recorded using International System of Units? Go ahead and choose all that apply. Write them down in your notebook. The correct answers are A, 107 meters, D, 26.3 kilograms, and E, 17.9 seconds. All three have base units in this SI system. If you have any questions about what was covered in lecture, please make a note in your notebook now and make sure you ask me at the beginning of class.